All right, welcome everyone. Apologies for the technical hiccup there at the start. It's my pleasure to introduce Lenka Zdebrova from CEA Saclay in Paris. Lenka works at the Institute for Theoretical Physics there, and she's done amazing work looking at analyzing machine learning algorithms using the statistical physics toolkit mathematically. And I think there's a lot that theoretical neuroscience can learn from these methods. There's a long history of using them in both fields. And so we're very excited to hear from her today on understanding machine learning via exactly solvable statistical physics models. And just to orient you, please feel free to ask questions anytime in the chat or through the Ask Question button, and I'll be monitoring that, Lenka. And if you pause, I can summarize any questions that have arisen. All right, and with that, over to you. I'm going to put your slides up.
Okay, thank you, Andrew, and hi to everybody. I'm very happy to be at the Neuro theory seminar, although my talk and is really not so much concerned with neuroscience, but clearly neuroscience played a big role in the field that currently is called machine learning or deep learning, and is probably going to continue to do so for a while. And there is also the other direction of the machine learning being kind of so powerful these days that there's a lot of it to be used in neuroscience. So this is just part of that cross-pollination. So here is a slide with my collaborators, and the ones in blue are the ones that are particularly involved in the things that I will be showing you. And so what my talk is involved with is this very basic question of how can we understand the machine learning, deep learning that we are seeing today, that is clearly brought unprecedented empirical and engineering progress into many applications, and I'm sure you have seen many of them. And this includes fundamental sciences such as physics or neuroscience. And as a theoretician, we want to understand how does that work. So the three very basic and key questions that kind of summarize that come from this article that I have found around a year ago. And I will go through them a little bit. What's really striking about this article, that it's a piece that Leo Breiman wrote in 1995, so 25 years ago. So while so much has happened in the last 20 years on the engineering and empirical side, on the theory side, we are still kind of discussing these questions, and there is no consensus and no final answer yet. What's the actual answer? So let me just go quickly through them to kind of set the stage of what are the theory questions that we are asking these days in machine learning. So the first one on why don't heavily parameterized neural networks overfit the data. Here I use a picture from a somewhat recent paper of the organizer, of Andrew, that kind of reminds to you this classical bias variance trade-off that we learn about in like basic statistics. That is when you try to fit a function that would be the red function from samples that would be the red points, and you use too simple of an ansatz with too few parameters, which would be on the left. The fit doesn't quite look well. If you use the somewhat right number of parameters, then it looks nicely. And if you use too many parameters, then you're perfectly in the function, then you're perfectly going through the points, but you're not generalizing well in the sense that out of your points, you're not at all close to the function. And this is a classical concept in statistics. The kind of puzzle of deep learning is that it completely defines this concept, and it's not only deep learning, but if I show you the full picture from Andrew's paper, if you go to even more parameterized function that has way more parameters than you have number of points, and you use very basic methods to fit, it looks good back again. So the more parameters you have, the better the generalization error gets. And that kind of a puzzle was coined under the name double descent in the recent literature in machine learning. This is a picture from a paper by Misha Belkin, where as the capacity of the model, or the number of parameters you can imagine, is increasing, the error goes down and up and then down again. So why is that happening, and how generic it is? Now you can ask me, how is it possible? These were recent papers. How is it possible that Reo Breiman asked that question already in '95? Well, because the very classical paper on what it is, the bias variance trade-off, actually had a figure in there doing experiment with neural network and realizing that that kind of the bias variance dilemma is not quite observed in a neural network. And they said that, you know, it doesn't fit the framework, but they don't understand why. And well, we still don't fully understand why. And, you know, this picture doesn't have the peak, it just has the decay as the number of parameters or hidden units increases, but also the peak that happens close to the place where if you had random labels, you would start to be able to fit them perfectly, was also observed in the literature. But I will come back to these things a bit more in detail. The other question about what is the effective number of parameters, that, you know, translates to the, you know, another way to put it is to talk about the sample complexity. That is, how many samples do we actually need to be able to learn, say, some task. In this case, you know, I give here the example of the SafePart 10 dataset, where you are simply learning from 50,000 examples of pictures to classify them into 10 classes that are specified here. And, you know, the current, say, competitions and state of the art is evaluated on these 50,000 samples. That is 5,000 per example, per class. But we don't really know whether you can do it with smaller. Or if I give you a goal, like to have an error that is smaller than something, we don't really have a theory that for an example like that would tell us what is the smallest number of samples that is needed so that this error can be achieved. And so that goes back to the effective number of parameters, or the sample complexity. So that's a very basic question, and we don't have a satisfactory answer in general. And moreover, kind of, you would think, oh, but learning, you know, people studied learning theory and things like that for 30 years. So surely there are some mathematical results that are relevant to this question. But actually, this kind of well-known these days paper from a few years back is showing that kind of the workhorse of the learning theory that is based on the VC bounds and the Rademacher complexity, that it is actually not providing useful answers. And the way the paper does it is very elegant and very actually simple. All they do is that they experiment with the current state-of-the-art neural networks, and they show that even if the labels of the pictures were completely reshuffled, so, you know, airplane would be randomly set to be learned as a dog, for instance, then the loss function that you're minimizing during the training can still be optimized to 0 error. And how is that related to the you know, failure of these bounds? That's actually a simple realization that flows directly from the definition of the Rademacher bound that, you know, maybe in physics or in neuroscience, perhaps. Yeah.
Can I just, one question? Can you click the hide button? There's a little banner saying Crowdcast is sharing your screen. If you click the hide button, we'll be able to see your whole display.
I see. But I don't see my mouse.
You don't see it.
So
oh,
I don't know how to click it. Yeah. Yeah, now I see.
There it is.
Okay, so I do hide and I go back full screen.
Yeah.
Okay, good.
Thanks.
So just for those of you who, you know, maybe many of you not familiar with what the Rademacher complexity is, you know, if you are familiar with the spin glass and perceptron literature, so it's actually something very, you know, not closely related by a simple relation. The Rademacher complexity is related to the ground state of a perceptron that has random labels. So this is a simple realization that, you know, I haven't seen it in the literature from the 90s or before. So something that we wrote a paper about recently. But this plus the learning theory on how the Rademacher complexity translates to what the generalization error must be doing, you know, this combined with the previous paper tells you that, yeah, indeed, these kind of concepts are not really saying anything useful about the current state of the art networks and their generalization error. And this brings me to the third question, which is about the backpropagation heading for local minima. So backpropagation here is just the name for the gradient descent algorithm on the loss function that one is optimizing, minimizing during the learning. And this loss function is highly non-convex. It lives in high dimension. It potentially can have exponentially many local minima, some of them bad in terms of the generalization error, some of them good. And for reasons that still are not fully understood, in practice, on the practical examples, the algorithm actually goes to the good ones. So how the theory literature approaches this, well, one kind of line of works is to show, oh, maybe the loss function of the deep learning is something special, that it actually does not have local minima. So here if you type no local minima deep learning, these are kind of the top hits that Google Scholar gives you. But that actually seems to be maybe a bit too theoretical, because if you look at it more carefully and relate it to this issue of overparametrization, it seems rather that the state-of-the-art networks, they actually do have many, even global minima, because the loss function is minimized to 0, and some of them generalize well, and some of them don't. So it's not about the absence of local minima, it's really about the trajectory that the algorithm is taking to finding the minima that has good properties. And this, kind of capturing this in theory, that's still a puzzle. So why are these questions that are so old, 25 years ago, still open? What is kind of the core difficulty here? So the way I like to put it is that in order to understand what goes on in deep learning, one needs to keep in mind 3 ingredients here. One ingredient is the architecture of the network. That is, how many layers do I have, how wide they are, what are the activation functions, and basically all these parameters describing the architecture. And the other ingredient is the algorithm, that is minimizing the loss function, and what exactly is the variant of the algorithm. And the third ingredient here is the structure in the data on which one is actually performing the task. And a lot of existing works, and I am a little bit provoking here, but even the subfields that study machine learning, the theory subfields, can be kind of divided. They focus on one of these sides, but not really on the 3 of them together. But focusing on the 3 of them together is crucial, because, of course, if we don't consider the algorithm, well, then we are maybe talking of problems that are exponentially costly. So we need to keep in mind that we want to learn tractably. And if we are not focusing on the structure of the data, then we would be considering some kind of worst case data. But from the theory of computational complexity, we know that learning even very simple neural networks is actually algorithmically hard. So for worst case data, there cannot be positive results in a sense. So there must be some particular property of the data that enables tractable learning. And if we put aside the architecture, well, then we are kind of putting aside the whole recent progress that tells us that there is something special about the deep feed-forward or other neural networks, that the depth seems to be important. So we better keep that in consideration as well. So that's the key difficulty here. So now that's where, that's where in my talk I want to bring the physics in. But I start with this kind of a, with this XKCD that many of you probably seen, just to warn that we don't want to end up in the case of this XKCD joke, that there indeed are things that physics is meaningfully bringing here. And I just say it in 2 items, the models and the methods. So I will start with the models and explain what I mean by that, and the methods, they will kind of come naturally just after that. So So when we say a model in, say, data science or statistics, we actually mean something very different from what we mean in physics. So this slide is just to kind of highlight the difference. So in data science or machine learning, the neural network itself, the architecture of the neural network, kind of the function that we are fitting on the data, is often called the model. And in physics, I would rather call that an ansatz, because that's something that is really supposed to fit the data nicely, kind of take into account all the details of some particular data set. And in physics, when we build a model, like for instance here, the Ising model, we don't necessarily want to keep in all the details. Like for instance, the Ising model doesn't have in any quantum mechanics, any particular details about Maxwell equations or magnetisms or any particular materials. It's a very simple prescription for a probability distribution, basically. Yet, among physicists, we kind of agree that Ising model explains the phase transition in magnets from the ferromagnets to paramagnets. So we kind of want to keep the essence of the puzzle, but put away the details that are not necessary to keep the essence. So this may be philosophical, but never mind. So what would be such a model for neural networks? So in the physics literature for already 30 years, the kind of basic model for supervised learning that has been studied is this teacher-student kind of framework for neural network. So it's the following kind of data set. You consider a teacher network. So here, for instance, I choose 3 layers, 2 hidden layers. On the input, I have the data X, and the data on the input, I just generate them as random IID noise. So the samples are independent from each other, and also each sample has components that are just randomly drawn Gaussians. So that's the most often considered case. And then how are the labels generated? They're generated by postulating some ground truth values of the weights that I call W star here, and using the feed-forward neural network, the teacher network, to generate the labels. And then the student network sees the inputs X, the labels Y. If you want to make the things simpler, you can also show to the student the architecture of the teacher network. That is, how many layers, what was their width, what were the activation functions. But crucially, it doesn't see the values of the weights W star. And the goal of the student network, or the question here, is, can we learn the same function as the one represented by the teacher network simply from the examples X and Y, from the pairs of inputs and outputs? And how will that ability, for instance, depend on the number of those samples if we want to, attack this question of sample complexity? And so in this simple case where you don't even have any hidden units, that would be, the model that is called generalized linear regression in statistics, or the PERCEPTRON model in statistical physics. This teacher-student variant of the PERCEPTRON, as I was saying, is actually coming back to the works of Gardner and Derrida in the physics literature in the late 80s. And they in particularly introduced this model and studied it in the regime where the dimensionality of the data xp is high and the number of samples is also high, but the ratio between them is actually some constant, say 5 or 0.2 or something like that. And that in statistics is called the high dimensional regime. That's already, kind of advanced statistics. Statistics would usually take the dimension p very small, 3, 5, something like that, and then send the number of samples to infinity. But taking both of them to infinity with fixed ratio, it's mathematically more challenging. So actually, to solve it, statistical physics literature actually solved this problem in the sense that they computed the optimal generalization error that any algorithm can achieve, basically back then, just year after, in this paper of Geza Georgi, that is in particular for teacher that is using the weights that are binary, in which case the generalization error that is drawn here has a phase transition. So this is something that typically in physics, we would be happy to see and want to study it. And so in order to obtain this curve, they used what is called the replica method in statistical physics. It's kind of a heuristic method used to compute these kind of things. But when, historically, when mathematicians would be faced with this method, they would just be concerned because there is assumptions being done during the calculation that are completely not justified mathematically. So for years, we actually didn't know how to actually show that these results are correct. So this is not true anymore. In a paper that we have put out a few years back, we actually closed this kind of a in mathematics open problem, but also this kind of frustration of physicists of using a method that never made the mathematical friends happy. That we established that this result that can be obtained for the optimal error for the perceptron is actually correct, and not only for the cases that appeared in the literature before, but for any activation function, for any prior on the weights. We also linked it to the performance of the best known algorithms and provided the proof. So I will be showing you some results of that, but before doing that, I just want to clarify. I use this, this term, the optimal generalization error. So what do I mean by that? It's, if you are used to think about training neural networks, you usually write some loss and minimize it. But and sometimes one forgets that that's actually not the best way that you should do if you actually had much more computational power. If you had more computational power, and especially in a situation such as the teacher-student model, where you actually know how the data were generated, then what you should do instead of minimizing a loss, you should write the posterior of what are the unknowns, the weights in our case, given the observations that are the data and the labels, the y and x in our case, and to obtain the optimal prediction, then rather than minimize some function, you would sample this function and average over all the possible weights with the weight that corresponds to this posterior measure. So that's the base optimal prediction of the new label. And you can prove that no algorithm can improve upon this one. And it's not the same thing as doing the empirical risk minimization. So that's what was analyzed back then, and that's what we analyzed in this simple teacher-student perceptron. This picture is for the case where the teacher weights are just Gaussians, so spherical perceptron, the probability of W's is just a Gaussian. And I'm showing you was the generalization error on the test set as a function of how many samples we have per dimension. So this parameter n over p. And the red curve, that's a result of the theory. The black points is the result of the approximate message passing algorithm that asymptotically in the limit is shown to agree with the theory. So indeed, we see that here, even for some intermediate sizes, it agrees. The blue squares, that's the result of a simple logistic regression that is doing nothing as fancy as sampling the posterior and evaluating the optimal labels the way the base optimal estimator is doing it. The logistic regression is simply taking the logistic loss and minimizing it with gradient descent. And yet you see that it's not so far away from actually the optimal error. So that's kind of a good case. And it was a little bit striking to us, so we kind of digged into it a little bit more very recently and asked ourselves the question, can the logistic regression actually reach the base optimal? And the answer is no, but it's no by a margin that is basically here on the right, that it's of the order of 10 to the minus 5. So if actually on the left you compare the black curve, that is the optimal error, and the orange crosses, that is the result of the logistic regression with optimized regularization and nothing more, you actually don't even see the difference. It seems that it is reaching the optimal curve. And the blue curve in that picture that gives so much higher error, that's just to visualize how loose the bounds that we know from the learning theory, the bounds based on the Rademacher complexity, how far away from the actual result they are. And even the decay as alpha goes large of the base optimal error is like 1 over alpha, and the Rademacher bound is quite universally 1 over square root of alpha. So even the rates are not agreeing with each other. So if that was always the case, that logistic regression is basically giving us base optimal, we would be done and probably we would not be here speaking about things. So already for the binary perceptron, there's the figure that I have already shown from the old paper of Georgi. If we take this case where the theory predicts the optimal error is the red line, and the approximate message passing algorithm is actually not, is matching it, except in this region that I call here hard. And the logistic regression is not quite at all capturing that there is something interesting happening at sample complexity that is 1.234, something like that. So it's not, but that's maybe not surprising because it's not knowing that the teacher used binary weights. But okay, could be talking about this for long. But maybe going back, this is still a neural network, or if you want to call it a neural network, with no hidden unit, so very simple one. But I wanted to tell you something about deep learning. So this is this bringing us towards the theory of deep learning? And going back to this picture, just so far, I told you something about architecture with no hidden units, algorithm that was not the gradient, well, logistic regression was with gradient descent, but the algorithm, the message passing was not the gradient descent. And on the data, on the side of the structure of the data, I was talking about IID inputs and teacher outputs, so that seems to be far from some realistic structure. Instead, we would like to be talking of multiple wide layers and gradient descent based algorithms and structured data. So can we do better? Can we go from the blue to the green? So that's kind of what has been occupying me for the past, say, 3, 4, 5 years. And so how are we doing in these different directions? In, say, in my group, or more generally in the statistical physics theory of learning. So on the side of adding hidden units, so one thing that we can do, and that again goes back to the physics literature in the 90s, is to add hidden units. And that would go to a variant of the teacher-student model that is called the committee machine. And we can solve it using similar methods and prove it using analogous proofs when the number of dimensions p and the number of samples n are both large with a fixed ratio that's the same as before. And now the number of hidden units needs to stay of order 1. It cannot really go large. It needs to stay of order 1 so that the theory holds. And in this case, but we have hidden units, and we can already, and so this, as I said, goes back to the literature in physics. 2 years ago, we kind of wrote a paper in analog to the paper that I was showing you about, where we proved that the replica formula is correct, made the link with the performance of the approximate message passing algorithm. And already in this case, we can observe some quite interesting behavior that that has been there already in the works in 90s. Notably here in the simplest case that has hidden units, that's 2 hidden units, you observe the specialization transition that makes a nice kind of a point of something that is often seen in practice, that if you do not have too many samples, then it's usually not advantageous to use deep learning. And something much simpler, such as kernel regression or some other variants of linear regression, actually do the best job. And the specialization transition is basically a model to explain this behavior. And even in this case of 2 hidden units of the committee machine, we see a sharp value of the parameter alpha, at which if we had fewer samples than that, then nothing can do better than linear regression. And only if we have more parameters than that, we can take advantage of the 2 units and actually they will actually specialize to the 2 hidden units in the teacher, and the generalization error will improve at that point. So
can I jump in with 2 questions for you that we've had?
Sure.
So first, Ilya has asked, what do we know about the structure of data that can be generated by these type of teacher networks? Like, what does it look like coming out of that?
Yeah.
And second, this is more specific to these plots, the ones just before. I think the question is essentially, what is AMP versus logistic regression? Is one minimum mean squared error and the other one maximum likelihood?
So the first question will be addressed just in few slides, so wait for that one, right? In my triangle, I will go around the triangle and show you the 3 sides. For the logistic regression versus AMP, so yes, AMP computes the minimum mean square error. Logistic regression in this case is not even the maximum likelihood. It's just, it's just the first thing that one would try if one had like a simple binary classification problem, and it just happens to do really great. So, that a practitioner would find if actually I like gave him this data, didn't say anything where it comes from, I would take scikit-learn and try logistic regression, but it's not the maximum likelihood in this case. Okay, so to go on with that, maybe skip that. So on the committee machine, kind of anticipating what I want to be telling you about the structured data, we can also analyze. So the previous slide was about the approximate message passing, kind of as the base optimal algorithm for accessing the best performance. In the committee machine, we also know how to analyze the stochastic gradient descent for, again, already 30 years or so by works of Sad and Sola and followers. And also recently we kind of, this is going back. Recently we kind of put that theory also on a rigorous ground and proved that these equations are correct, and also generalize them to the case where the student actually has more hidden units than the teacher. So that's the over-parameterized regime, but I'm just giving here the reference and kind of referring you to the paper. So in this case, we know how to analyze the stochastic gradient descent that is not seeing any sample again, so kind of the online version of it. And with this, go back to the triangle and kind of update the side of the architecture that we know how to deal with few hidden units. Other works can do more, but pay something else. Like for instance, in deep linear networks, one can do more, but one forgets the nonlinearity and other approaches. But kind of if with this kind of approach of applying, say, the replica method and computing exactly the partition function, etc., we wanted to approach the case where the hidden layer is extensive. That would be a scaling limit that makes sense. But it's an open problem how to pull off the calculation in that case. We don't know how to solve that yet. So people are looking at it, but it's challenging, and there is no even heuristic theory for that case at the level of the precision that we had for the previous cases. And so let me look at the 2 other sides, because that's I covered the side where we kind of maybe currently know the least. Well, we have still big job to do. But on the other sides, so the algorithms, I will just show you a list of recent references and tell you that if you asked me, say, 2 years ago, I would tell you that we understand very little about what the gradient descent is doing, that we only understand well the message passing algorithms. But this is not true anymore due to series of works from last, say, 2 years. Of my student Stefano Manelli and collaborators, where we actually managed to analyze in a closed form the gradient descent. First in a model that is not quite a neural network, but where we kind of build the methodology for that. And more recently, that would be the last 3 references here. Actually, in this generalized linear model, so the perceptron and related models, we actually have a closed form for the trajectory of the gradient descent, from which we can, by looking at different cases, deduce a lot about its behavior and also its differences with the message passing. But that would be for the rest of the talk, but instead I want to spend the rest of the talk on the third side that also somebody was asking about the structured data. Because here, having IID inputs, that's really like very unsatisfactory. And while kind of the question of, we should study the gradient descent rather than message passing is very natural and has been out there for a long time, the fact that the data should be structured was kind of looming in the background, but not really addressed like so very often in the existing works. So how do we proceed with to address that part? So here, just to motivate, right, how do the structured data look like? So here you have some like pictures of people, but these are actually fake people. These are people that don't exist. These are pictures that were generated by a generative adversarial network that, the way it is trained is one thing, but the way once it is trained, what it does is that you have a feed-forward multi-layer network into which you feed random noise, and at the output you get these kind of images. And of course the weights, you train them, so you chose them so that the network produces these kind of images. But you see, it's basically a machine that from random noise produces this. And when we do something like a calculation within statistical physics, we need some kind of a randomness. So the idea is, okay, but isn't something where we feed in randomness and then it has some structure, isn't this something actually approachable? And you will see that it is. And kind of what this also motivates, that actually when you have the generator of the GAN, the input into that feed-forward neural networks is usually much smaller in dimension than the output dimension. So this is telling you that these complicated pictures of people actually live in much lower dimensional space than is the output, than the number of pixels, which would be the kind of output of the generator and input of the next neural network dimension. So here I try to depict it that, if you were kind of randomly sampling point in your input dimensional space, you would get this kind of random noise. But if you only sample meaningful images, there is a much lower dimensional manifold on which these images lie. And okay, this is not new. These dimensions of these manifolds are being measured, estimated, etc. But this is kind of the basic idea that we want to keep to construct a better model for the input data. So with this in mind, and with the fact that in mind that the generator of the generative adversarial network is just a feed-forward neural network, multi-layer, let's start with one layer and let's mimic the generator of the GAN. How would it look like? You would have some noise C. So C here will be a random IID matrix. That is what you're feeding into the generator. And then you will have some matrix of weights, F, that in practice would be learned. So you don't want that to be random. So here we take F as a generic matrix. It will have to, in the proof, then satisfy some conditions, but it can be pretty much anything. It doesn't have to be random. Then you feed it through a nonlinearity, because that's what the feed-forward networks do, right? Multiply by matrix, feed through a nonlinearity, etc. And we stop here because we just consider one layer as the simplest case. And so this F times C feed it through a nonlinear function, little f, is giving us X that we will be using as the input data. And how are the labels generated? The labels are generated by a teacher network that is acting, but not on the axis, but on the latent representation C. So okay, I will go back to this. So maybe let me show it in a picture. So we call that the hidden manifold model, because here I depict like the input space would have 3 dimensions, but the manifold that we consider has only 2 dimensions. Then the matrix F would be representing kind of the low dimensional subspace where the manifold lives. And then the matrix C would be representing the coordinates of the points that we will be then classifying on the manifold, on the submanifold. And then the teacher that is generating the labels actually acts on these coordinates on the submanifolds and decides on the submanifold where kind of the cats and dogs are lying. So like, for instance, here. And then the submanifold gets folded in a sense by this nonlinear function little f. That is coming once my slide wake up. And oops, I jumped too much. Oh no. So okay, never mind. So then this space gets folded, and that is the application of the function little f. So what is interesting about this hidden manifold model, so far I just, okay, why not generating data this way? Oh, okay, sorry, here is the slide that I jumped over previously. So it gets folded, and then the resulting coordinates, that's the input data x. So what's interesting about this model are two things. One thing, as kind of my title is highlighting, this will be a solvable model, and I will show you how we solve it in a moment. But the other interesting thing is that actually it reproduces some behavior of learning on real data that the simple teacher-student model that we have been studying for 30 years is not reproducing. So one of these behaviors is, this specialization to phase transition that I was already mentioning with the committee machine, that we can actually see in MNIST when we train simply a very simple neural network that in this case has just k hidden units, and k are the different curves, so 1, 2, 4, or 8, on the MNIST dataset, where we are trying to classify odd digits from even digits just to make it binary. And the error we are getting as a function of the number of epochs is shown here. And you see that with just linear regression, which is if we have only one hidden unit, that's equivalent to linear regression, we do something. And then as we are having more and more hidden units, at the beginning of the learning, we kind of follow what the linear regression would do, and then only we start to get smaller errors, so learning something better. So one can say that the neural network learns a simpler function first, and then only learns something more complicated gradually. And if you do the same experiment in the hidden manifold model, we see pretty much the same thing. So that's one interesting thing. But this is maybe something that we still can reproduce with the classical teacher-student model. But this next picture is, we cannot reproduce it with the classical teacher-student model. And that's the following thing. So again, one picture is for MNIST and one picture is for the hidden manifold model. What I do here with MNIST is the same task, but this time we train two student networks independently, meaning that they have an independent initialization, but otherwise the algorithm and all the other parameters are the same. Okay, and this learns two functions, and now we are asking how different or similar are these functions. So if we compare these functions on the test set, they mostly agree because we learned something. So on the test set, on most of the examples in the test set, they are correct. So that also means that they must agree with each other. But if we actually compare their output on a random Gaussian noise, which never appears in the actual test set, but we can just construct it and compare these functions on a random Gaussian noise, then there's the green curve. Then we actually see that if we are learning with more hidden units than some number here, 3, then the two functions will basically agree only at 50% of cases, which means that they are just random to each other. So that's kind of interesting that already such a simple neural network with just, say, 4 hidden units on the MNIST dataset is able to pin down where the submanifold is and learns a function that agrees on the submanifold, but out of it basically didn't learn even anything, learn something random, because even the two functions learn independently from each other basically disagree. And if we do the same thing on the hidden manifold model, we see the same behavior. So that's a point for the model, that it reproduces something that we see in realistic cases. So now I was saying, the kind of from the theory point of view, what we love about this model is that we can solve it with the kind of same precision as we were used to from the simple perceptron model. So in particular, this is our work, but it's also, of course, as always, building on some previous work. So these are related works by the group of Andrea Montanari, where they provided a solution for a very related model that basically ends up to be a special case of what we have done for the case where the matrix F is random and the learning is done just with least square regression, not with not including hidden units, and also with max margin regression. And we solved it so in two cases. One with the case where we look at the online learning, so when the samples are coming online one by one, and we could generalize the work of Sad and Sola to this model. And the third point is that in the batch case, that is where we have all the data at once, then we also have the generalization, say, of the Gardner or Georgi replica formula to this model. So how comes that the way we created the matrix X is kind of very correlated? So how comes that the theory that always needs to average over randomness is kind of able to pull this off? So there's actually an interesting kind of property here that we call the Gaussian equivalence, that states the following: that the learning on a model as we created it, that is, if the X is created as a function F on a product of two matrices, one random and one arbitrary, that the learning on such a model in the limit that we are considering has the same properties as learning on a model where the nonlinearity F would not be there, and instead, I would this equation of the X mu with would be some constant kappa 1 times the matrix F times the matrix C plus Gaussian noise plus some other constant. And the second model is actually much more comfortable for analytic tractability. And the fact that learning on these two models is the same is kind of surprising, is not at all trivial. And so we argue it in kind of the theoretical physics rigor in the papers from the previous slide, but more recently in a paper that is submitted but still not on arXiv, we prove that this is actually true in this case. And this is just a slide to show you that, okay, the replica saddle point equations to write the generalization error in this model, they just look kind of non-intuitive, but for those of you who know them, the same as usual. So I will not be really explaining in detail, just to say that, the thing that maybe is the most surprising on this solution is that it doesn't require the matrix F to be random, that it can be arbitrary. And the only property of the matrix F that enters in this replica solution is actually the Stieltjes transform of the matrix FF transpose. And so we need to have the matrix F to be something where we can analytically write the Stieltjes, or at least numerically write the Stieltjes transform, so that we can evaluate these equations. But otherwise, it can be up to some balance conditions, can be arbitrary. And then, the other highlighted points is that it, of course, depends on the loss function Lx of y, and it depends on the function on which we on the prior, and on the function on the nonlinearity that we use to fold the manifold. It depends only through these constants kappa 0, kappa 1, kappa star. So not there is also some big kind of a universality with respect to these activation functions. And then, I will be slowly going towards the end by showing you some results of how this hidden manifold model behaves. So this would be a phase diagram of when we take the hidden manifold model with the nonlinearity when creating the data, that is just the error function, and the labels are creating by teacher on the latent space that is just generating sign of the scalar product between the coordinates in the latent space and some teacher weight, W0 here. And then here I'm looking at classification with just a single layer neural network with the least square loss. And I am plotting here the generalization error for lambda is the regularization, just the ridge regularization in the least square loss. And here, it's kind of the similar picture to the ones that we have been seeing at the beginning, is that as the number of samples is growing, the error is going down, but in the non-regularized case, so when the lambda is small, there is actually this interpolation peak popping up. So it's not quite monotonic. It actually first goes down and then, first goes up and only then it goes down. So that's analogous to this picture I was showing from the papers by Opper in the 90s. And the heat plot on the right is showing, you know, what is the error as a function of, so the x-axis is the good old number of samples divided by dimension. By the y-axis here is the latent dimension of the submanifold divided by the input dimension. And the fact that, you know, the error is good when the number of samples is very small and d over p is also very small, it's kind of telling us that even this very simple learning method is able to kind of find the hidden manifold in the data and find that there is this structure, even though this is not even a neural network. This is the simplest possible one, just single layer least square regression. So this is what we are seeing in this model. And, you know, next two slides are, okay, because you could see, is this the double descent behavior? So not quite, because the double descent, the y-axis, I would have to have the number of parameters. And here it's kind of upside down. The number of parameters is small when the x-axis is small, not when it is big. So to kind of show you that, yeah, I can just like transform the solution of this hidden manifold model into something that shows the actual double descent, I just need to reinterpret a little bit what the hidden manifold model is for those of you who know about learning with random features. So learning with random features, that is learning with one hidden layer neural network, where the first layer of weights is just fixed and random. Not necessarily IID random, but it's not learned. Crucially, it's not learned. And only the second layer is learned. So that's a neural network that actually ends up equivalent to kernel methods if the hidden layer is very wide. And this is actually the case that has been studied in those papers by Montanari, where kind of their solution was very related to ours. So if you think, you know, here I just wrote again what the definition of the hidden manifold model was, but here I need to reinterpret it to get the random feature learning. Here the C should be the input data, and the matrix F will be the features, and then the X will not be the data, but that will be the projection to the higher dimensional space, and the Y will be labels here produced by the traditional teacher as before in the simple teacher-student model. And so if you think about it this way and then plot things as a function of P, P is the dimension of this vector X, so that is the number of dimensions in which we are projecting in the random feature learning. So here it is the number of parameters divided in this case by n. Then we kind of see, depending which loss we are minimizing, whether it is the square loss or logistic loss, we see this double descent peak and the decay as the number of parameters is going to infinity. And the peak is at different places, depending which loss we are using. It's always at the point where either the square loss is able to go to 0 for even random labels, or for the logistic loss, the data gets actually linearly separable. So there are some interesting relations here. But just to go towards the end, this is something from like very still not on arXiv either paper, but we were kind of wondering, you know, does this hidden manifold model, can we make it deep, and does it, you know, can we make it deep, and can the matrix F, or if it is deeper, there will be several of them, can they be learned from the real data? Can we actually, this theory, can it extend to data that come from actual generative models that were trained on real data sets? And this is much more challenging question, but in this last work, we actually found a way to do it. So far, you know, what we managed to do is to generalize the Sardan-Sola equations. So these are differential or ordinary differential equations that describe the behavior of the stochastic gradient descent when the samples are coming one by one. And kind of theoretically, we have justification of those equations for deep generative models where the weights would be independent from each other and not learned. But then when we use the same equations and did experiments with something that is learned and that has a lot of structure, that is not at all random. So here I'm showing you an example with this is some close to state-of-the-art generator of CIFAR images. That that paper of Radford et al. From 2016, we just took their their trained model and then use it as a generator for the data, for which then we are analyzing the gradient descent on the committee machine. And here are the details of how the generator looks like. And here, that's a comparison between our theory and the performance of the committee machine with data that come from this generator. And on the left, we are using the generator with convolutional matrices, so convolutional layers, so a lot of structures in there, but the parameters are just random. And it fits perfectly our theory. But also for the case where actually the weights are trained on the actual CIFAR, it fits the theory. You see that not perfectly, but kind of the deviation that is there, that's a finite size effect, because the input dimension to this network is actually quite small. But otherwise, we are capturing the trend, which is pretty interesting. And kind of to persuade you that it's a finite size effect, here we took yet completely another generative model that has a lot of structure. This is based on normalizing flows, and again, we just took the train generator from the literature and generated the data with that. The normalizing flow is an invertible neural network. That means that the input dimension is not small, it's actually as big as the input space. So in this case, it was something like 3000. So there we could reduce the finite size effects. And if we take this network, so we generate very structured data. And we have a set of ordinary differential equations into which we feed just some correlations computed empirically from the data. And they describe to us how the dynamics is behaving. And I'm not really explaining what these curves are. These are the different order parameters that are popping up in the ODs. But okay, I can tell you more about that if you're interested in the question time. But with that, I will finish, and thank you for your attention. And if there are more questions, I hope there are question time.
All right, thank you very much. Let's thank Lenka. I suppose you just have to do that by clapping in the chat or something. We do have questions. Let me kick off with a few. So first, we have a question about how to find the manifold dimension. So I think your theory, presumably, that's a free parameter, but I suppose the question would be, could you use these findings you talked about to sort of suggest a dimensionality for a specific data set? Yeah, you want to start with that?
Yeah, so the works that are kind of estimating the dimension of the manifold, we were not really focusing on this, but the way they do that is basically by looking at the density of points locally and kind of estimating, how many points you should have at given distance in a certain dimension. So that's kind of the basic idea of how people estimate the dimension of the, say, MNIST data set. And there they conclude that it's something between 10 and 20, depending on which particular method they use. Now, whether we could use our results to estimate the dimension, well, as Andrew was correctly saying, for in the model, this is just a parameter. And when we compare to the real generators, there it's kind of a the input dimension is kind of given by what was the network with which the generator was learned. So people kind of tried many, and there was one that worked better. So whether the input into whether the one that works best is a kind of decent estimator of the dimension, well, it's certainly a bound, right? If it works well, then the dimension cannot be bigger than that. But yeah, I'm not aware whether actually people use that to estimate the dimension. One could, I presume.
And maybe one quick follow-up on that. Is there any link between these off-manifold differences between functions and something like adversarial perturbations, or have you looked into these types of phenomena?
Yeah. Yeah, the adversarial perturbations, that would rather be that, that kind of going, that you don't have to go far away from the manifold to get completely wrong. Whereas we are kind of far away from the manifold and we are kind of surprised, or, realizing that the functions have nothing to do one with another. That means that kind of the learning process somehow managed to pin down the manifold of the data. So it's a little complementary. Yeah, I don't see like any direct relation, but maybe there is one.
All right, and then question, what happens in the limit when the sample number goes to infinity slower than the network size rather than with network size?
When the number of samples goes to infinity slower than the network size? Yeah. Okay, so I'm not sure I'm understanding. So if you're just in the case without hidden units, then the network size is just like the dimension. So then it would mean that alpha is 0, so we are not learning anything. So the question probably meant the network size in terms of the hidden units. And yeah, okay, so that will be actually, so I would rather put it the other way around. Like, what happens if the hidden layer is so wide, is so big that the number of samples is like much bigger than the hidden layer? That's a slightly different regime that people study under the name of the mean field limit, kind of when the network is very wide. So yeah, so you can study that. What happens, it depends what one is looking at. It's a different limit. I mean, if you go from one to another, everything is compatible, but things, for instance, for the random feature learning, you simply go to what the kernel. I would have to have more details, like what the person meant with that question. Or maybe I answered. If I didn't answer, please ask with more details. Are we still there?
Sorry, I managed to mute myself.
Oh, okay.
So maybe we can go back to this question which I asked early on about what we know about the structure of data that it's possible to generate using a teacher network. And I suppose there's two ways to interpret that. One is if you were allowed to choose any weights, but the other one would be, is there something particular about drawing those weights from Gaussians which is, you think, is realistic or not about real data sets?
So there are two sides of when we say, drawing the data from the teacher network, right? There are the inputs and then there are the outputs. So when I'm thinking about this question, like what can we draw from the teacher network, it's basically about the correlations between the outputs and the inputs. So yeah, okay. What was the question again? What happens? So I'm just saying that there are these two things, and we here concentrated on the structure of the inputs. That we don't want those to be IID because that's very that's as I was showing, that's kind of not realistic, and somehow the fact that the labels should depend on some latent representation of the inputs rather than simply on the scalar products of the inputs with some random weights seems important here, but I'm not sure whether that answers the question. This is difficult if I don't even see the person who asked the question. Is he happy or she?
Yes, I think they are. You might get a follow-up email. Okay, and another question. when comparing two students on Gaussian data, how do you incorporate symmetries into the weight matrix? I'm not sure I'm getting exactly what that question is. Maybe it's about...
Yeah, so we don't do anything special about incorporating symmetry. So for instance, when we do the experiment on the ConvNet, I mean, they are just the convolutions, so the symmetry is kind of incorporated there. In the, yeah, that, so yeah, maybe that's here, like one additional surprising thing that the equations that we wrote kind of doesn't depend on that, whether it's a convnet or fully connected net or generating or normalizing flow. We don't do anything special about the symmetries. We just take the networks as they were trained, and then the input to the equations is just the correlation matrix of the data that they generated.
Mm-hmm. Yeah, it's really quite striking. I have to think about what that means, that these trained models actually you can still describe the dynamics.
Yeah, me too. I mean, it's kind of, yeah, I wanted to show it because it's like it's amazing that it fits, but why really, and what are really the conditions under which it should fail? It's kind of eluding me at this point.
Mm-hmm. The question about whether you've tried applying your methods to data other than images. So I suppose that could be the GANs, but it could also be the manifolds model. Do you see similar results on phoneme recognition?
Yeah, so that's a really good question, and we definitely should, but no, so far we only tried the images and you know, just like data that just come from some random, completely unstructured input. But yeah, that's a really, I mean, that's kind of a very important generic question, right? Which of the kind of salient fact that everybody knows about neural networks are only true for ImageNet and CIFAR and MNIST, and which of them are kind of true more generally? Yeah, we should be asking the question more, but unfortunately, I don't know yet today.
All right. We'll wait to see if there's one last question, and I'll just ask one. So I guess I'm curious what your view is of, so you briefly mentioned the neural tangent kernel style results. Maybe you could just like put that in relation to what you've shown us here and how you view those results at the moment.
Yeah, so those results would go about like linearizing the neural network around the initial condition and basically showing that there is an equivalent kernel method to what the neural network would be doing before it goes too far away from the initial conditions. So, you know, it's a beautiful theoretical playground to ask questions, and then there is kind of an ongoing debate whether this regime is rich enough to describe the, you know, the puzzles that we are seeing, or whether kind of the fact that it is just equivalent to a kernel, so it's not intrinsically learning any features, whether it's actually, you know, kind of eventually making it not so relevant. So my take on this, that it really depends. It might really depend what's your kind of intrinsic dimension here. Because when you ask whether a kernel method is powerful enough to learn something or not, the way I like to think about it is that kernel method is basically just a fancy nearest neighbors classifier, right? The kernel is just reweighting kind of your neighbors, but it's a nearest kind of morally it's a nearest neighbor classifier. And so if your space is truly high dimensional and you really only have number of samples that is proportional to the dimensionality, then you're just no way filling that space so that something like nearest neighbors can be useful without any feature learning, right? So in that regime, feature learning can be able to do something, but kernels just cannot. Now, as I was, you know, saying even in this talk, the real image data sets that we are looking at, they don't seem to be so low high dimensional. Like if it is true that the MNIST is effectively only, say, 10 or 14 dimensional, well, then maybe the fact that we have like 50,000 samples is actually filling close enough that 14-dimensional space that the kernel method can actually do something. So I think there is still some like zoology of regimes in which we in which we are actually asking these questions that should be looked at more carefully. Maybe, the works that seem to be disagreeing on that, like, is feature learning necessary or not necessary, maybe they are looking at complementary regimes. At least that's what kind of it seems to me currently.
Mm-hmm. Interesting. Yeah, I guess a related question in my mind is, I think a lot of theoretical ideas have said, oh, deep networks work well because we sort of compose simple functions together again and again and again. But the story that you've shown so far, I mean, I know it doesn't do anything like ruling that out, but you are showing the power of having underlying manifold structure, which doesn't really seem to have that composing simple functions together and again and again kind of structure. So I'm just curious if you see any connections there.
Yeah, I think this is largely because, when I was showing my triangle on the deep side, we are not so good yet with like our kinds of methods. That I think if we could analyze the deep, the multi-layer networks really kind of with, in a simple closed form way, I think that would be a wonderful way to kind of probe this question, how composing the functions is important. And I think it is important for the very, physically intuitive reason that the natural data will be multi-scale and the different layers are kind of taking care of the different scales. This to me, this is just an intuition that many people put up, but to me this seems a very solid intuition. So getting kind of on the bottom of that, we would need a better analysis tools for these deeper networks that we so far do not have. So I guess what I'm just showing that some of the puzzles that are out there and kind of sometimes presented as puzzles of deep learning, that many of them actually already appear in like shallow learning or even like regression. And I'm not like they have, there is a good amount of work kind of going in the similar direction. So to understand deep learning, we also need to first understand properly the shallow learning, because we just maybe didn't look at it into detail enough to actually see that some of these paradoxes are there already.
Yeah, I completely agree. Okay, final question to end on. Does your comment about the relation between kernels and k-nearest neighbors apply in equal measure to translation invariant kernels and dot product kernels? Or could it be that the success of inner product kernels has to do with the different notions of locality? So, yeah.
Well, of course, the thing is that if you kind of, the kind of feature learning that neural networks are, I think, intrinsically doing, we can also engineer the features and plug them into the kernels. So if we do that properly, well, okay, then what I said will not quite be true. But then we are kind of in the signal processing field 20 years ago when we are engineering the wavelets and the Fourier transforms. So that, of course, is a valid way to do it that has great successes. But that doesn't seem to be quite what deep learning is doing. So yeah, there may be classes of kernels that that behave differently because one kind of hand engineered features into them. That would be my answer.
Right. Okay. Well, thank you very much, Lenka, and thank you for everyone for joining. And yeah, see you at the next Neurotheory.
Thank you for all the questions.